In this video, we're going to be discussing an introduction to the use and applications of mass spectrometry. First, as a totally random move, here's a small riddle for you, the answer of which will be randomly placed throughout this lecture. What runs around a backyard but never moves? Okay, in previous lectures, we have been discussing how to obtain structural information and actually draw Lewis structures given IR spectra. But consider all of the problems that we were given. We were always told what is the empirical formula of the molecule or given additional information. Consider if you were just given this IR spectrum and told to draw an explicit structure based on that IR spectrum. Now, it's true, you may be able to obtain some structural information. For example, you could look at this and say, I see CH stretching, and I don't see anything here, and I don't see anything here, so I know it's a saturated hydrocarbon. I could look at this big peak and say, oh, this saturated hydrocarbon has a carbonyl. In fact, I might even recognize that this compound is probably an aldehyde. But trying to figure out what the exact structure is would actually be impossible. There are lots of different saturated aldehydes. In order to obtain the actual structural information, the minimum information you would need would be the molecular weight. If I told you the molecular weight of the compound was 88 grams per mole, or 88 AMU, you might be able to start figuring out what structures could possibly exist. You do that based on the fact that you know you have 12, and then you have 16, and you have 17, and then you'd start trying to figure out how many other carbons and hydrogens you might have and what kinds of things might exist. You could come up with a short list of things that might fit that bill, but it would be difficult to say the least. But you could certainly narrow the list, given at a minimum the molecular weight. If I told you the specific chemical formula, then it would make it even easier. But still, you could probably only reduce it to a few or a number of different isomers. What would be really nice is if I gave you the empirical formula plus additional structural information. Then you could probably identify the exact isomer that generated that IR spectrum. Ultimately, that is the purpose of mass spectrometry. Mass spectrometry, first and foremost, is to provide you with molecular weight information. Second, it can provide you with empirical formula information so that you know what elements are there. And third, it can provide you with structural information. Because of the uniqueness of the information provided by mass spectrometry, we will also see that we can do library searches. Which can actually identify the compound. This is the purpose of the mass spectrometer. Just as a quick introduction to what a mass spectrum is, mass spectrometry was originally developed by J.J. Thomson. If you remember, J.J. Thomson was the person who determined the mass to charge ratio of an electron. He did that because he knew that if you took a charged particle, whether a positive or a negative, and you put it through a magnetic field, that the magnetic field will cause a force, specifically the Lorentz force, at 90 degrees to its velocity vector. This means that ions will be, well, effectively blown off of a straight line course. They will be deflected by the magnetic field. The amount of the deflection is inversely proportional to the molecular weight. That's not illogical. Consider that if you have a very heavy basketball or medicine ball being thrown in one direction with a breeze blowing perpendicular to it, the angle of deflection would be very little. If you have a light molecule with low momentum, that same crosswind could blow it to a higher amount of deflection. In this way, the magnetic field operated similar to a prism with dispersion of molecular weight from high mass to low mass. You could identify which mass almost in the same way that we determine the wavelength of light from a dispersion. This allows us to scan through and look at what masses, just like what wavelengths, are present. Just like an absorption peak, we would see which ions exist, which masses exist. We would see peaks at different mass to charge ratios instead of peaks at different wavelengths of absorption. If three different molecules existed, weighing 36, 44, and 58, then we would see three different peaks corresponding to the masses of those particular molecular weight molecules that existed in the sample. The answer to the riddle, by the way, is a fence.